All right, hi everyone.
Hi.
Thanks for joining us on Memorial Day, right? Miroslav, do you want to introduce Andy?
I can do that. Okay, so welcome everyone. Today we're happy to have Andy Neitzke, who's going to tell us about Abelianization of flat connections and its q-deformation.
So thank you very much. Thanks for the opportunity to speak in this seminar. So I'm going to describe joint work, partly in progress. Part of it has appeared. So work partly in progress with Fei Yan, who's at Rutgers. And this work is sort of broadly connected to a circle of ideas that have a lot of people have worked on. So, but in particular, a lot of the ideas originate in work of Kontsevich Soibelman, of Fakh-Goncharov. Some of the ideas come from my earlier joint work with Davide Gaiotto and Greg Moore, but this is an area where a lot of people have contributed. So let me start out with just kind of a word cloud of the talk. So the central idea that I want to discuss is something called Abelianization, which we'll see what it is as we go, but just in a few words. So by Abelianization, I mean the Abelianization of flat connections, and what it is roughly a way of taking problems that have to do with connections for a non-Abelian group. And for me, the non-Abelian group is going to be GLN, and relating them to something much simpler involving the group GL1. So a non-Abelian group, and you replace it by an Abelian group. So it's roughly a fancy version. The easiest example of this is you have a generic matrix and you can diagonalize it. This is something that we do with a flat connection. It's with a whole bunch of matrices. You can't literally simultaneously diagonalize them. You can, that's what this Abelianization. And it's connected to various other things. So in particular, the interesting things that it's connected to, and which these days I think is the most interesting way to motivate it. And so that's the method that I'm going to use to kind of motivate this construction. It's connected to exact Wkv. And what I like about that is just something about equations. It's something that you might care about even if you don't care about anything. And so my point of view is going to be that you start out with just some question about differential equations, and it forces you to think about this Abelianization. Then the Abelianization is connected to various other things. So it's connected to plus coordinates. You think of those as a particular way of studying flat connections. It's connected to an algebraic geometry, and Thomas invariants, maybe generalized Thomas invariants. The way that we first got into the subject is that it's connected to supersymmetric quantum field theory, mostly n equals 2 supersymmetric quantum field theory. And then it's connected to some particular functions of flat connections, which are called. So if I would just stop there, this is a story which I and collaborators have been working on for a few years now. But the real thrust of this talk is summarized in the quote up above, which I think is a relatively famous quote now from a book of Edinov, Frankel, and Kirillov. I thought I was clever in having this quote. I heard that Mina actually used the same quote in her series of talks a few weeks ago. Anyway, I think it's a nice quote, so I'll give it here. And so the basic idea is that many mathematicians at some point get the Q disease, which is you discover that all the things that you're interested in admit a Q deformation. So the first stage of the disease is you learn that, and the second stage of the disease is that you become obsessed with the idea that the Q case is actually much more interesting than the classical one. And so in this story that I'm going to tell, there have been a lot of hints that there should be a Q deformation, just because many of the subjects here already have a Q deformation that people know about. So the Donaldson-Thomas invariants have a upgrade to motivic Donaldson-Thomas invariants. Cluster algebras have a quantum version, so the cluster coordinates can be upgraded to quantum cluster coordinates. And the trace functions have a natural Q version, which is polynomial link invariance. In supersymmetric quantum field theory, you can study supersymmetric quantum field theory keeping track of spins of particles or not. You do keep track of the spins, that's a kind of q-deformation. And so knowing about all these things, you might start to believe that there should be a q-deformation of abelianization, which you might just call q-abelianization. And in this work in progress with Fei Yan, we've made some progress toward developing what that is. So that's what I want to explain. So in this talk, broadly speaking, we're going to cover this part of the diagram. Okay. One thing that I don't know, and in a way what I think would be one of the most interesting things, is what's the Q version of exact Wkv analysis. So I think there's a lot of hints that there should be such a thing, but on the other hand, we don't really know yet what that is. Okay. So, all right, enough general stuff. Let's get started. So I'll start at the left of the diagram. I'll start with exact Wkv. And this is a story, as I said, that's been developed by a lot of people. So it goes back to Vertex, Yale, many people. More recently, it's been reinterpreted in the language of cluster algebras, and particularly good reference that explains this is work of Wkv Method. Recently, I have a paper with the Hollands where we describe it in a way kind of close to what I'm going to say in this talk. So okay, let's start with something concrete. Let's start with the Riemann surface. Let's take the Riemann surface to be CP1, or it could be a more general Riemann surface, but then it should have a CP1 structure. So you won't lose much by just thinking of CP1. And let's fix a meromorphic quadratic differential. I'll write it as P of z dz squared. Meromorphic quadratic differential. Let's see. And let's also fix a complex number, which I'll call h bar. And then given that data, there's an equation, a second order linear differential equation. So in local coordinates, here's what it looks like. D squared by dz squared plus the potential rescaled by power of h bar. So there's a second order differential operator, a second order scalar differential operator just acting on functions. So we'll just let it act on functions. So we'll call that equation star. So you might call this a meromorphic Schrödinger equation. I guess usually you would study the Schrödinger equation with a real parameter. So instead of z, you might write x and have it on the real line or something. So this is like some kind of complex continuation of that. Okay. Now, another way that's convenient to think about this equation, let's rewrite it. There's this standard maneuver when you have a second order equation, a second order linear ODE, you can write it as a first order equation, but for a vector instead of a function. So I'll write it like this: d by dz, and that's going to be a first order equation, plus this little 2 by 2 matrix. There's an operator, and now it acts on a vector where the first component is the original psi of z, and the second component is its first derivative. So that equation, if you just expand out its two components, one of the equations is just psi prime equals psi prime, and the other component gives you the equation star. So this equation is equivalent to the equation star. When you write it that way, you can think of it as the covariant constancy equation for a flat connection. So this operator here, this matrix operator, you can think of as being a flat connection depending on the parameter h bar. So we'll call it nabla sub h bar. It's a family of connections depending on h bar. Each one of them is a flat SL2C connection over, well, over not C, but C prime, which is C minus the poles of the potential. Okay, so we started out with writing out the Schrodinger equation, but we can also think of that as being some SL2C connection over our surface. And suppose that we want to understand this Schrodinger equation. Well, what does it mean to understand the equation? You might say what it means is you want to understand the solutions. Of course, the solutions in any example that's at all non-trivial, you won't be able to write down the solutions in any kind of closed form. They're not functions that have names. So what concretely could you hope for? One thing you could study is not the solutions themselves, but their monodromy as you go around loops on the surface. So that's a relatively concrete thing. The monodromy around any loop is going to be some 2x2 matrix up to conjugation, right? So let's fix a loop. Let's fix a loop on C prime. Then we might want to study the monodromy, which I'll write whole L of nabla h bar. So as I say, that's a matrix up to conjugation, so it's still a little slippery to get your hands on. One thing that's really invariant would be the trace of that matrix. The trace of the holonomy. Okay, that's some honest function. Well, for any fixed h bar, that's just a complex number. As h bar varies, this is some holomorphic function of h bar. And so you can just ask, what is that function? So if someone gives you the potential P of z, and the question is, what is that? Yeah, and sorry, someone gives you the potential and someone gives you a loop. And now the question is this function. Okay, and this problem is kind of closely related to the usual problems that people ask. And this might seem like a slightly unfamiliar thing. The more usual things that people ask about Schrodinger equations would be things like, where are the bound states? You know, for what values of the energy do you get a bound state? This problem is very close to those kind of problems. So I'm phrasing this one for simplicity. But the techniques are somehow techniques. Okay, so how would we try to address this question? Well, there's a method that was, I guess Wkv goes back a long time. Every undergraduate learns it in their quantum mechanics course. Every physics undergraduate learns it in their quantum mechanics course. But there are a lot of sort of thorny technical things about it, which have gotten worked out over time into this so-called exact Wkv method. So the exact Wkv method is the following. You write down solutions of the equation in the following form. You have to write down a psi of z obeying this Schrodinger equation up at the top. And the way you write it is like this. You write, it's going to be the exponential of something. What is that something? It'll be 1 over h bar times the integral, starting from some z naught up to z of, okay, square root of minus p, I'll leave a little space, and then dz. Now, if I just wrote this, actually this, exactly what I just wrote here is what you might first write. Like if you're an undergraduate in your first differential equations class, you might write exactly this because, you know, is this a solution of the equation? Let's see if this is a solution of the equation. Have to take 2 derivatives of it, right? And the first time I take a derivative, I pull down h bar inverse times square root of minus p. The second time I take a derivative, I pull down another h bar inverse times square root of minus p. So that's great, right? I got minus h bar squared, minus h bar to the minus 2 times p. So it's exactly a solution of the equation written at the top, right? The only reason why that's wrong is that the second time you take a derivative, you have to differentiate the thing that you pulled down the first time. And for that reason, this isn't exactly a solution, but that error is of lower order. It's of order h bar to the -1. So in the limit of very small h bar, this would really be a solution. That's why you would first be led to write this down, is in the limit of very small h bar, this is actually correct. Well, of course, it's not exactly correct. But so what this would lead you to do is maybe you can just fix it up by adding higher and higher powers of h bar. So the idea is that that's the beginning of some series. And then you fix it by adding some from 1 to infinity of some other functions of z times h bar to the n. And so that's something you can really do. You know, you just substitute this ansatz into the equation, and to leading order it's satisfied as we saw, and then to higher and higher orders you just iteratively determine these functions Sn. So that gives you a solution of this equation. And then of course, once you understand the solutions of the equation locally, you can kind of patch them together globally to calculate the monodromy. Now there's one subtlety with this, which is the reason why this method is kind of tricky. The subtlety is that the series that I've written down here, so it's a perfectly good formal series solution, it always has 0 radius of convergence, meaning that this is not an actual solution. But there's a machine for dealing with that. You can use this tool called Borel Summation. So here I better write Borel resummed. And so now there are theorems available that say that, there's always a caveat that I forget to mention. Let's assume, and I should have written it up at the beginning, so maybe I'll go back up to the beginning. Let's assume that P of z has at least one pole of order greater than or equal to 2. So there's some technical assumption which is required in order to make this whole machine work. But with that technical assumption, you can actually Borel resum this series, you get actual local solutions, and you can use them to calculate the monodromy. So now, what's the geometry of this setup? Well, one thing you notice right away is that these solutions, in some sense, they don't live naturally on the surface. They live naturally rather on some double cover of the surface. Why is that? Well, it's because in writing down the solution, the first thing I have to write is I have to write the square root of minus p, right? I wrote square root of minus p. P is some holomorphic function. It's not the square of anything, typically. It doesn't have a global square root. But in writing down these solutions, I have to choose a square root. So that means the solutions don't naturally live on the original curve, but rather they live on some double cover of the curve, which is just the Riemann surface of the square root function. That Riemann surface naturally sits inside, since P was globally a quadratic differential, if I keep track of how all the objects transform, this double cover is naturally sitting inside of the cotangent bundle of my base curve. So the picture would be something like this. So we're studying an equation here, but the solutions that we construct are most naturally thought of as living on some double cover of it. And it's a branch double cover, and the branch points are the zeros of this potential. So zeros. So this we might call spectral curve. Okay.
What over the poles? Is it a?
Oh yeah, so the pole. Sorry, I didn't mark a pole. So suppose there's a pole here. Then the two sheets of the thing are just going off to infinity at the pole.
So it has the covering has punctures at the poles.
That's right. That's right. I guess it's a covering. So C twiddle has a 2-to-1 map to C, but the image of that map is the complement of the poles. The image of the map is C prime. That's right. Okay, so by these kind of considerations, here's what you get. So here's now the theorem. So we wanted to study this function, the trace of the holonomy, That's our starting point. We have the Schrodinger equation that we want to understand. And we want to study the trace of the holonomy around some loop. And the theorem is that you can describe it completely in terms of objects living on the spectral curve. That's what this exact Wkv method leads you to. And what that description looks like is the holonomy gets expanded as a sum of kind of more elementary things, which I'll write that sum like this, and then I'll explain what the symbol means. So first of all, there are some integers, just some weights, and then there are some functions. So I have a function on the left, and I'm expanding it in terms of functions on the right, which I'm saying are somehow better. So here are the properties. So first of all, what is L Twiddle anyway? L Twiddle is running over loops now on the cover surface. So we started with a loop down on the base, and the answer is going to come out in terms of loops on the cover. And in fact, these functions on the right don't even depend on the exact loop, they just depend on its homology class. And now the functions that we expand in, we can actually say something about. In particular, we can say how they behave for small value of h bar. So if you were interested in this function, one of the first things you might want to know is, what's its expansion around small h bar? And the answer to that is that as h bar goes to 0, say along the positive real axis, you just get, you get this sort of classic, irregular, how do you say it? Essential singularity, exponential of 1 over h bar, or exponential of some constant over h bar, where the constant that appears is the period. So it's the period of the kind of Liouville one form on the cotangent bundle, which in my coordinates here is just y dz. So you integrate y dz around the loop. Y was the square root of p. So another way of saying is, you have some potential, you have to integrate the square root of the potential around loops. In quantum mechanics, you would call that the instanton action. Okay, and the other thing to say about these functions, or one other thing to say about these functions, is that they're functions which have been seen before. So how do I think about these more elementary pieces of the monodromy? One way of thinking about them is that they come from some coordinates on the moduli of flat connections. So let me write M of SL2C C prime. So what's that? That's the moduli space of flat connections, flat SL2C connections over C prime up to equivalence. So to get this x gamma of h bar, what I do is I take some standard functions on the moduli of flat connections and I just evaluate them at the particular connection I'm studying, the connection that comes from this differential equation. Well, what are these coordinates? For generic P, they're usually the so-called Fach-Goncharov or cluster coordinates. So I don't know, there's some, I don't know how big a subset of the mathematical world, there's some subset of cluster aficionados who get excited when you see the cluster coordinates. So for those people, the thrust of what I'm saying is, look, you start with, well, I guess for everyone really. What I'm saying is that we started with a problem which was a naturally defined problem, had nothing to do with clusters or anything. And just in the process of trying to solve that problem, you're sort of forced to consider the cluster coordinates. They're the best variables for analyzing this problem. Okay. So that much is the theorem. Yeah.
Is the Poisson bracket of these cluster coordinates related to somehow the intersection pairing on H1C tilde?
Yeah, exactly. Oh, good. So what do I mean by saying they're Darboux? Yeah, so what I mean is exactly the following. Thanks, that's a good question. Let's move this down a little bit. Right, yeah. What I mean by saying that they're Darboux is precisely the following. The Poisson bracket bracket of x gamma with, say, x gamma prime. So if I take two of these coordinate functions that are associated to two different cycles, gamma and gamma prime, that their bracket is x gamma plus gamma prime times the intersection pairing gamma gamma prime. So in other words, there's some kind of, that's another way of thinking about this, there's some complicated holomorphic symplectic structure on the moduli space of SL2C connections. It's the Atiyah-Bott symplectic structure, Atiyah-Bott-Goldman symplectic structure. And then there's a much simpler symplectic structure on GL1 connections over the spectral curve. And this map from one is symplectomorphism. So in other words, maybe better just to say, at this moment, maybe better just to say, the Poisson structure, which usually is complicated, you can give by a very simple formula in these coordinates, and it's the formula that I wrote in purple here. Yeah, so that's another aspect of this thing.
And suppose I wanted the entire monodromy as opposed to just the trace?
Yeah, so there's a version of it also for the entire monodromy. The thing is, to even state what it means by getting the entire monodromy, you have to somehow specify a basis, right? Because otherwise it's only defined up to conjugation. So there is a more elaborate version of this thing where you erect actual distinguished bases. Yeah, in fact, since I'm talking about exact WKB, right? Those exact WKB wave functions that I was writing, doing Borel summation of, those do produce for you a kind of almost canonical basis. And so you can ask, what's the monodromy relative to that basis? And yeah, there's a good answer for that, where for L Twiddle, instead of having closed loops, I would have some open paths on the spectral cover. But yeah, there is a kind of parallel version of it for that.
So would you say that then you can basically solve these kinds of monodromy problems?
Well, I wouldn't quite say that you can solve it because, well, okay. To completely solve it, I would have to give you a formula for these functions x of h bar, right? I told you something about it. I told you its behavior as h bar goes to 0. I didn't write, but could have written a whole asymptotic expansion. That's still not the same as giving the function. But, okay, the very next thing I was going to say is that it is believed that you can determine those functions in the following way. Well, you can determine them like this, that they can be obtained as solutions of some integral equations, which are sort of like the thermodynamic beta ansatz, equations of TBA type. And in setting up those equations, excuse me, I'm having a very strange problem. Okay, better. Sorry about that. So those equations, you use basically just the data that I've described and will describe in this talk. So this is a story again with a long history. So it goes back to something called the ODEIM correspondence. Rose had some similar ideas. Then we wrote down equations sort of similar to this in the work with Davide and Greg. And then, but exactly this conjecture really appears in most clearly in a paper by Nato. And then subsequently, various people have developed it further. And for example, there are papers of Dylan Allegretti and Tom Bridgeland and Grassi, Marino, etc. So there is a story of the exact functions. That story isn't yet at the level of theorems, but that's certainly part of the philosophy here, is that you can really solve the problem completely using these ideas. Okay. So, okay, then let me say briefly, I've been telling you about Schrodinger equations, which is the case of sort of a second order equation. But there's a similar story for equations of order and greater than. So for example, for n equals 3, the parallel sort of equation that you would write would look like this. It's like a kind of Schrodinger-ish equation, but now it's of third order and it has 2 potentials instead of 1. So I'll just write the equation, h bar to the minus 3, p3. So it has p2 and p3. And then some weird little correction. So some scalar third order ODE. It has third derivative, first derivative, and no derivative. And so if you're interested in analyzing these kind of higher order equations, there's a completely parallel story where now the exact Wkb happens on a triple cover instead of a double cover. So you write an equation like this. And here, so that story is not at the level of theorems; it's at the level of conjectures. But the numerical evidence is pretty convincing that this method also works.
There's a condition on pole orders of P2, P3, as in n equal to.
Yeah. So again, it works easiest if you have kind of high enough order poles. Don't ask me exactly what it is.
It's not 3. That would have been the obvious guess, but okay.
No, there's some kind of coherent. It's a different condition on P2 and on P3.
I see. It's okay.
Okay. Okay. So now we want to start getting to the Q part of the story. So let me just kind of summarize where we are here. So now, even if you didn't understand anything I said, all you have to understand is the following thing. What were we doing? We had a surface C, and it's covering C twiddle. And maybe C was like just punctured CP1, so it might be like that. And C twiddle might be some higher genus surface, so it might be like that. And we were taking a loop. We were asking some question that had to do with a loop on the surface. So the question was, what's the trace of monodromy of this differential equation around this loop? And the answer to the question, in order to get the nicest information about the answer, we were led to consider loops on the covering, but not just one, it was a bunch of them. So it could have been like one here, one here. It was some finite sum over various loops. They might intersect like this. So the next thing I want to explain to you is, what are those loops? So, just the sort of syntactic form of this theorem is, you have a loop on the base and you turn into a bunch of loops on the cover. And you might ask, well, how do you do that, right? It's not going to be just literally the usual lifting the covering spaces. It has to be something more involved than that. Okay, so what are they? Okay, so here's how it works. And this is really the key part of this Abelianization process, is this process of taking a loop on the base and turning it into a bunch of loops on the cover. So here's what you have to do. So you make it out of pieces. Forgive me, I'm having another technical problem. Can you still hear me? Hello?
Yes, we can hear you, yes.
I see. My desktop computer has frozen with the annoying consequence that I can no longer advance my notes. Wait just one moment. Sorry for this. Naturally, a problem that you never have in your ordinary life always occurs exactly at the moment when you try to give a talk. I think I'll be able to solve this problem in just a moment. So let me start and hope my computer will catch up. So the problem that we want to solve is we're given a loop on surface C, and we want to relate it to a bunch of loops on coverings. And the way it's going to work is that the loops L Twiddle, which we use upstairs, are going to be built out of kind of elementary pieces. So the first thing you could do, maybe the most obvious thing, so here's my base, here's the covering. The obvious thing you can imagine doing some part of your loop downstairs is, and just lift it up to one or the other of the sheets of the covering. So, so that's kind of one thing you can do, and I'll call that a lift. But that's not the only thing you do. So if that was the only thing you do, then the story would be very boring. For some loops, wouldn't have lift at all, right? Because you could have a loop on the base, which when you try to lift it up to the cover, goes from one sheet to the other sheet. So it wouldn't really make sense for that to be the whole answer. So this is a second ingredient in the answer. And the second ingredient looks like this. Now I hope that I can get my notes back. Great files except for the one I need. Okay. So I'll go on for just a little bit. So the second looks like this. So here's C Twiddle, you see, and what happen is I'm going to have a little piece of my arc on the base, my loop on the base, which has a special point on it. And what happens is that at that special point, the lift is going to from one sheet to another. So these two are connected like this. And how does it happen? The way that it happens is, so the covering is a branch covering. So let me draw this. So here's a branch point. And so that's covering some point on the base. And what we have is this C Twiddle now inside of the cotangent bundle. And for this part, it's going to be actually important that it sits inside the cotangent bundle, because object in this, for the second kind of lift, is a special Lagrangian disk inside of the cotangent bundle. I'm drawing here, which is kind of like a bygone. It has part of its boundary on a cotangent bundle. That's what I'm drawing in red. And boundary is on this spectral curve C Twiddle. And so the rule that we allow is whenever there's one of these special Lagrangian disks inside of the cotangent bundle, then our lift is allowed to kind of hitchhike along the boundary of that Lagrangian disk. And travel to the branch point, go through the branch point, and come back on the other sheet. So let's call this, so this is a special Lagrangian disk. More exactly, say almost special Lagrangian disk. There's a little technicality, because the cotangent of C is not literally a hyperkill. So this is some special Lagrangian in some sense. Projection down to C is an interval on C that obeys a differential equation that's just determined by C Twiddle. So you should think of it as being morally a special Lagrangian disk. Okay, great. Now, okay. So that's the picture in the case of just two sheets. And then, so we call these detours, because the lifted path kind of, it follows the curve on the base, except L, this is L Twiddle, this is L Twiddle.
And the red dot is any point you pick?
That was, say it again?
The red point is just a point you pick, right? Or
well, no, very good. So, you know, these special Lagrangian disks don't occur that often. So they occur only in very specific places. So if you pick like a generic point on the base and you look at that fiber and you ask, is there a special Lagrangian disk, which is a bygone that has boundary on part on C twiddle and part on that fiber? The answer will be no, there isn't one. So these special Lagrangian disks only occur once in a while. They're sort of expected to occur at discretely many points along along your L, along your loop.
and it's important.
So
it's really important for you that it's special Lagrangian. I can't deform it a little bit. I can't deform the Lagrangian.
You can deform it, but no, I think it's important. Yeah, it's important.
So I'm just trying to understand this picture in terms of the class S theories. Over there, the branch points would be the zeros of the differential.
Exactly, that's right.
And the gray line downstairs would be a flat geodesic with respect to the, well, the projection of the side.
That's right. So that's right. So I could have said it in that language that, you know, the gray line downstairs is some trajectory, which is, yeah, we could say it that way. So this trajectory has the property that the, along that trajectory, the square root of minus p dz is a real one form. That's equivalent to this condition of being an almost special Lagrangian disk upstairs, is the condition that its projection to the base is a trajectory obeying this differential equation. So that's right. So that's the picture for just two sheets. And for more than two sheets, there's a similar picture. Here, I'll just draw the picture down.
Andy, isn't this a little oversimplified? Can't you have a more complicated soliton spectrum?
Well, for n equals 2, generically, you don't, right?
No, but you can.
For n greater than 2, of course, you do.
Yes,
I was just about to draw
n greater than 2, but even for n equals 2, you can have more than. These are just the simple. In terms of the soliton spectrum on the surface defect, these are just the simpletons, but you can still have more complicated things. You can have more complicated things.
For n equals 2, for a generic quadratic differential, these are the only ones you get. But for n greater than 2, certainly you do get all kinds of other things. So, so I'll just draw a picture of like what the projection of that disk might look like. So you can have more complicated special Lagrangian disks whose projection is more interesting to the base, looking like this. Okay, and so so what have I told you so far? I've told you that we started out with this problem of understanding differential equations, and the solution to that problem that's provided by exact Wkv depends crucially on this procedure of lifting paths from the base C to some covering C twiddle, which is the spectral curve. And in that process, essentially the only thing that gets used is the geometry of the cotangent bundle in the form of these disks. Okay, so now I want to try to talk about the q-deformed version of this story. I want to talk about quantization. So in the story I just told you, I was studying the function of a flat connection, which is the trace of the holonomy. and I was mapping it to a sum of functions, which I could think of as functions of a GL1 connection over the covering. So I took the holonomy of a GLN connection over the base and replaced it with the sum of holonomies of some GL1 connection over the cover. So formalize this a little. You could say that what we were using was a homomorphism, I'll call it F, from functions on the space of GLN-C connections to functions on the space of GL1-C connections now over this covering. And now I want to describe quantization of that. So you can think either of quantizing the spaces of connections themselves. I mean, those are naturally, we wrote down the Poisson bracket earlier. There's a natural Poisson bracket which you can try to quantize. So, well, I guess that's the way to say it. You look at the algebra of functions on that space, that's some Poisson algebra, and you can try to quantize that Poisson algebra to a non-commutative algebra. And that's what we'll do. So what is that non-commutative algebra? Well, there's a well-known quantization, which is called the Skein Algebra. So here we'll have two variants of it. We'll have the GLN Skein Algebra. That's quantization of the moduli of GLN.
May I ask a naive question before quantizing this algebra of functions? This map F is injective. So basically you can pull back any function on GLN character variety to GL1C on C tilde.
That's right. Well, the map of character varieties goes the other way, right? This map, I mean, this map would be dual to the map of character varieties. So this is like a map.
Yeah,
if you think of it as a map of character varieties.
Map?
Sorry?
So sorry, so in what direction is the map for character varieties?
So the map from character varieties is you take a GLNC connection over the cover and you map it to a GLNC connection over the base.
I see. So it's the push forward construction, basically. You're right.
No, not the push forward. Okay, good. It's a kind of systematic correction of the push forward. If you literally do the push forward, it won't be a flat connection on the base because the monodromy around branch points, what you'll get is a connection over the base minus the branch points. So that's not what this thing is. So all the, if it was just the push forward, I wouldn't have had to mention all these holomorphic disks or anything. It would have been a much simpler construction. You can do that simpler construction, but it doesn't work.
Yeah, okay. Yes. I mean, you want additional
push forward.
Right. Okay. The reason I'm bringing this up in algebraic geometry, there's a similar map from the Jacobian of the spectral curve to moduli space of bundles on what you would call the ultraviolet curve. And that's a dominant map. But that's okay. It's not needed here. We can discuss that afterwards. I just wanted to confirm
let's talk about that later.
The direction of maps over here. So it's clear now. Thank you.
Okay, good. So we have this map between algebras of functions, and now we want to quantize it to a map between quantized algebras of functions. I'll call that F sub Q. So I should say quickly what the quantization is. So I think there's a lot of different variants of this Skein algebra. So what I mean by the Skein algebra is we take framed oriented loops in C cross R. Now we take formal linear combinations of those with coefficients Laurent polynomials, integer Laurent polynomials in the Q. And then we'll mod out by some equivalence relation. What's the equivalence relation? The equivalence relation is the following. There's a few relations. So one is, so in drawing the relation, I'm drawing just part of, oh, sorry, I wrote loops, but I should of course have written links. So I'm drawing just part of the link, and the convention will be that this means we consider links which are the same everywhere else except for this little part. So for example, here I have, on the left, I have an overcrossing, on the right, I have an undercrossing, and then there's one more thing. I could draw, which is this. And then the relation is that the first one minus the second one, so that's a formal linear combination of them, one minus the other, that's identified with q minus q inverse times the third one. So any three knots that differ just inside of a little ball, and in that ball they're related in this way, they have this kind of relation. So there's that relation. There's another relation which says that if I have the framed length like this, that it's identified with that one with a factor of q to the n. Now those two might first look the same, and of course they are the same if I think of them just as links up to isotopy. But when I think of them as framed links, they're different. So here I'm giving each one the blackboard framing. In other words, I think of it as a little ribbon, which is standing up vertically on the table. And then if I have the ribbon on the left and I pull it taut, I'll introduce one twist. What this relation says is that twist costs you a factor of q to the n. And then the last relation is that whenever I have a little closed loop, just a contractible loop inside of some ball, that I can delete that and replace it with this factor. Okay, so this is the Skein algebra. This is the GLM Skein algebra. Formal linear combinations of links modulo this relation. And so,
and the reason we are using this as opposed to anything else is what? I mean,
you mean as opposed to some other quantization?
Yeah, for example.
Well, this is the one which is supposed to be, I guess the good physical answer would be, this is the one which seems to arise as the algebra of line operators in class S theories. In other words, this is what we'll literally get by taking like the surface defects of the 2,0 theory and putting them in, putting them on these links cross R. So yeah, so as a practical matter, that's why we consider this specific one.
2,0 theory has lots of surface defects, including many which have continuous parameters and.
Oh, good point, good point. So here we're just taking, absolutely. Here we're just taking the very simplest surface defect, just equipped with the standard representation. We're not considering junctions or anything like that. So there's definitely more things that we could try to do. We could try to include on the left side of this map. That would make our job harder. So here I'm doing just the very simplest thing. But I agree, there's more natural things that you could try to put over on the left-hand side here, and maybe we should. In the ultimate version of this, you probably should.
Okay, can you explain one more thing? In this story, what informs the choice of your covering of C on the in other words, the choice of C tilde?
You mean from the point of view of the 2,0 theory?
Yeah. So the tension that I see there is the following: that you expect different sheets of the covering to start gluing together when you have well, what you literally said, surface defects of the 2,0 theory, which are codimension 4 things in 6 dimensions. Whereas in any problem that involves knots, you expect to have codimension 2 defects. So what's happening?
No, but here I'm not doing that. I mean, maybe you could do that, but I'm not doing that. I'm literally putting the surface defect of the 2,0 theory. I mean,
so you think of it as a codimension 4 object in the 2,0 theory.
Absolutely.
Okay, so we're from M theory perspective, we are thinking of like junctions of fibrines with fibrines, right?
I mean, there's different ways of realizing the. So to get the 2-dimensional defect, I should think of it as like the end of some M2 ring that comes in from infinity.
But you said the defects we want are codimension 2 or codimension 4?
Surface defect, sorry, if I said codimension 2, I didn't mean it. Surface defect.
So you mean codimension 4?
Codimension 4.
And so why do we then get this fancy covering of the Riemann surface?
Well, you're always free to, move out on the Coulomb branch of the theory. I mean, even without the defect, even without inserting any defect, right, I could study the theory on its Coulomb branch. That's what going to this C twiddle corresponds to. So I'm not thinking of that as being induced by the defect or anything like that. We can just take this theory and put it on its Coulomb branch. And then once we do that, we could ask questions like, okay, suppose you have some surface defect of the UV theory. What does it look like in the IR? In other words, what does it look like after we move on to the Coulomb branch? So the choice of C twiddle here is totally independent of the link.
Okay. And in particular, for all of our story, like the entire story, can we take just C tilde to be just an unbranched cover? There are no branch points whatsoever.
Yes. Yes, absolutely. So that's pretty boring from the point of view of the exact WKB when Q is not, when Q is just set equal to 1. But indeed, as I'll say at the end of the talk, hopefully, this story, this q-deform story is interesting even when C is just the complex plane. And the covering is just like, you know, n disconnected copies of the complex plane.
Okay, and now going back to exact WKB, what's Z?
What's, you mean capital Z, the period?
No. The coordinate in respect to which the differential equation is written.
Yeah. So that's the coordinate along the, you know, in the class S story. That's like the internal curve.
And what does it mean from perspective of the lines that you're drawing? Or from perspective of your defect?
So I mean, what can I say? The setup is we're taking, you know, you could say it's the 2-0 theory on the Riemann surface C cross R4. Or you could say it's M theory and the cotangent of C cross R7. And the line defect, well, the surface.
And yeah, I'm asking something very simple. Since we could take C tilde to be completely unbranched, why did we start with the WKB?
Yeah. Well, no, in WKB, that's what I'm saying. So the exact WKB will never produce for you this unbranched thing. So the exact WKB was the story at Q equals to 1. At Q equals to 1, the unbranched case is kind of boring. And so that unbranched case will not arise in exact WKB as far as I know. But the unbranched case does arise once you turn on this Q parameter.
Great, thanks.
Okay, good. I'm sorry, I'm in a little disadvantage here.
It might help to say that spectral networks can be defined for any branch covering. I guess you're sort of saying that.
Oh, absolutely, yeah. You can take the C twiddle to be anything. Anything sitting in any branch covering sitting inside of the cotangent limit.
But it might not arise from the Coulomb branch of some 2-0 theory.
Okay. And H bar, are they related in some way? H bar and Q, are they related?
No, it doesn't seem so. So, okay, so I think your question is about sort of how would we put these two things together, right? How would we put the exact WKB story together with the quantization that I'm describing? It looks like the story is that those are just two independent parameters. So it has H bar and it also has Q.
I think what you want to do, Andy, is instead of your exact WKB, you want to study a very special equation, which is the Knighting's homological equation, where Q and the H bar are related. Now, of course, this will have different monodromy properties than the thing which you get from generic surface defects, which are codimension 2 in the 2-0 theory as opposed to codimension 4, which you need for knot theory. And it's natural that a very special equation arises in that problem. I think that's the one you want.
Okay, well, it would be great to talk about that further.
I think what's behind a lot of what Andy's saying is a relation to Hitchin systems, not Knighting's homological. if you know a relation between conditioning examologicov and Hitchin, then okay. But a lot of what's behind what Andy is saying is the relation to Hitchin systems.
Well, to be truthful, one doesn't need all of the details of the conditioning examological equation. Like, for example, the gauge choice we were talking about may not actually be the entirely essential part of the problem, right? And so there are analogous equations that would, I think, arise from Hitchin systems if you were to relate the Hitchin systems to, say, double algebras, or in this case, I guess, Virasoro, the way Techner does in many of his papers. So we could replace the intricacies of conditioning examological equation in this context with the special defects of Liouville theory, and or rather, it's Karl Hauff, and then you would get scalar equations, which you could recognize them as analogs of conditioning examological equation, just in this, undoing the step we did, which is starting from a nonlinear differential equation to a linear higher order differential.
Since I don't think I'll be able to say anything quickly that's relevant to that story. So maybe I should finish describing what we did do, and then maybe come back to this question. Let's see. How am I for time here?
Andy, we are flexible with time always. Hopefully our people joining us are flexible too, but these seminars are typically extremely time flexible. So,
I see.
Yeah.
Well, okay. So as I say, I'm a little at a disadvantage that I can no longer see anyone. But let me go on for just a little bit to at least explain more fully what this story is. So
if you would
what I
like
was
to
trying
just
to do
take a
is,
minute or two break and like reconnect, because I imagine that it may be annoying to be at such a disadvantage.
oh God, that would be
could
fantastic.
Just wait a minute.
Is that all right? Yeah, let's do that.
Yeah.
If you'll forgive me, let's see if I can solve my problem here. Great.
So meanwhile, just again, a naive question. So when you say one should be using KZ equations, is it really KZ or QKZ, the Q version of them, which are difference equations? Just
Well, okay, we need to wait for the end of Andy's story.
yeah,
probably
no,
he's trying to connect to it's just conditioning examological.
I see.
What's behind it? I think the important part is that for this kind of not clear type problems, all you need is the braiding matrices, and you can get braiding matrices in many different ways.
No, that.
In other words,
you want the quantum group hidden somewhere behind this thing. That's it.
Exactly.
All right. Can you hear me? Okay, good. All right. Thanks. So let's carry on with part 2. So I was talking about quantization of some map between character varieties, between the GLN character variety of a surface and the GL1 character variety of its spectral covering, or in general, just some n-fold covering that sits inside of the cotangent bundle. So that map I kind of motivated from considerations of exact WKB, but now that we have the map, we could forget that it comes from exact WKB and just the question, is there a natural quantization of this map? And that's what I want to tell you. So I was first to tell you about the quantization. I have to tell you about the quantization of the space. So I told you the quantization of the moduli GLN connections is this GLN Skein algebra, and there's a parallel quantization for the GL1 connections. So no big surprise here. It'll be again linear combinations of framed oriented links now in C twiddle cross R, the covering, with just a slightly simpler kind of relation. Well, it looks slightly simpler. It makes a big difference in how simple the algebra actually is. So the relation now is that you can change a crossing just at the cost of a power of q. So before you had to do something more complicated. You had to consider sums of different things. But here you can change the crossing. You can change an overcrossing to this. You can resolve it at the cost of a power of q, or change it to an undercrossing at the cost of a power of q squared. Then again, there's this thing with the framing, where now the framing costs you just q. And there's a thing with deleting a little unknot. And in this case, deleting the unknot, you do it for free. It just turns into number 1. So that's the GL1 Skein algebra. So in practice, because you can use this relation to just change all the crossings, the evaluation of the class of any particular link in this GL1 Skein algebra is very, very simple. It basically reduces to just computing the self-linking number of that link. Well, you get the self-linking number, and you still keep track of the homology class of the link, but only the homology class, nothing else. And so this algebra is a much simpler algebra, and it's sometimes called the quantum torus. The quantum torus built on the first homology of the cover with its intersection pairing. That's another meme for this GL1 Skein algebra. Whereas the GL algebra, as far as I know, doesn't have another name. It's this slightly complicated looking algebra. Okay, so my goal now is to produce a homomorphism from this GLN Skein algebra of C to the GL1 Skein algebra of the cover. And so the theorem now, which for n greater than 2 is still in progress, so theorem in progress. So this is joint work with Fei Yan. It's closely related to things that have been done before, so particular Bonahone and Wang, in the case n equals 2, had constructed more or less the same map, but in a very different way. And then there's also closely related work in the physics literature. Gabella and Galikov, Wang, and more. So the theorem is that, well, such a map exists. So a map of Skein algebra exists, such an FQ exists. And it's of the form very similar to what I wrote before. A link gets mapped to some bunch of links on the covering. Now think of this as, so you start with the element of the Skein algebra that's represented by just a link in the surface cross R, and you map it to an element of the Skein algebra which is represented by some linear combination of a bunch of links in the covering cross R with coefficients that are, some of the Rand polynomials in Q. And how do you construct this map? So it's constructed very much in the way that the classical map was built. So two of the pieces are exactly the same as what we had before. So we had these, what I was calling direct lifts, where you literally just take the link and lift it up to the cover, some part of the link, lift it up to the cover. Then there were these, what I call detours. They came from special Lagrangian disks, or as Greg says, solitons. But now there's a new thing. So the new ingredient, the only new ingredient that you need in order to go to the q-deformed story from the non-q-deformed story is this kind of diagram. So, okay, sorry. So I'm going to have, again, this. And again, I'll draw the n equals 2 version of it first. So here's my base. Here's my covering, which sits inside of the cotangent bundle. And so now this is going to be a phenomenon that involves two parts of the link. So I've got my link and two different arcs inside of that link. And what they're going to do is the lifts are going to change places. So, yeah, did I draw it right? Yeah. Okay. Oh, no, sorry. Right, I did not draw it right. So one lift is going to teleport over to here, and the other lift is going to teleport over to there. And so how does it do it? Well, it'll be these two special red points corresponding to this point and this point. So two fibers of the cotangent bundle are involved instead of one. And the key object now is, again, the kind of approximate special Lagrangian object, but now it's kind of a strip instead of a disk. We draw a strip like this, whose boundary is one path going like this, one path going like that. So we include that kind of, so another kind of detour that you can take. Again, you take a detour along the boundary of this special Lagrangian object, but now instead of being connected, it's two disconnected things. So these pieces of the link are kind of exchanging their positions. So this is almost special Lagrangian strip. So these objects we call exchanges. And again, so that's the picture for n equals 2. For n greater than 2, we have to consider also kind of higher webs. So you can have pictures that look like this.
So there's no branch points in this picture, are there?
There's no, that's right, there's no branch points involved in this. It has nothing to do with branch points, and therefore it can occur even in the case where there's no branching. So, even in the case where the covering is true. Oh, but one thing I should say, sorry. Of course, this is not just happening in C, it's happening inside of C cross R. This is C twiddle cross R. It's inside the cotangent of C cross R. So,
are you just rewriting sort of the action of quantum group R matrices? Basically interpreting like the spin up and spin down in terms of the
story from this thing.
So
yeah, okay,
is
so
this a reinterpretation, or can one discover this directly from physics? If you had, suppose nobody told you about it, would you have been able to discover it from your spectral networks and so forth?
Would we have been able to? I mean, there is some counterfactual universe where we discover it that way. I mean, we would have to be more clever than the actual us, but like, I don't see why it's. I don't see why it's impossible.
I think the answer, Andy, I think the answer is yes, because it has an interpretation in terms of soliton degeneracies on
no, absolutely, absolutely.
defects.
That's right. Sorry, I should be a little more.
It's a certain kind of soliton that you can even see in Landau-Ginsburg models, which are related to these not invariance and not homology.
I think that, I mean, this is just something about, another way of saying it, this is just something about the physics of the strings in the 2, 0 theory. In principle, you don't have to know anything about quantum groups. And some evidence of that is that I don't know very much about quantum groups. But nevertheless, we're able to make this thing work. Yeah, so this is the picture. Now, let me say just a word about these vectors. So each one of these lifted diagrams comes with a factor, and that factor is built from various pieces. So particularly the most important piece is that there's a factor q minus q inverse to the power n-1 for every web that has n ends on the link. So for example, for the simplest one, the exchange, the factor is just q minus q inverse. And so in particular, it equals 0 when q equals 1. And so that's the reason why this story reduces to the previous story when q equals 1. It's kind of systematic to that. Then the other kind of factors that are involved, I'll just mention there's a factor which is q to the winding number of the link L Twiddle. And you might ask me, what does it mean, the winding number, since it's a link in 3 dimensions? And the answer is there are various in this setup where you have L Twiddle living on this covering C Twiddle cross R, with various canonical projections to 2 dimensions, and you have to use the winding number in those projections. And then there are some other technical factors related to the framing of the links. Okay. Okay. So that's the construction. That's what we've constructed for n equals 2, and we know some parts of for higher n. Let me say just a little bit about the uses of this thing. Like, why would you want this thing? So one of these goes to Mina's question. Suppose we would just take the very simplest case where our surface is actually just the complex plane, and our covering C Twiddle is just given by a bunch of constant one forms. So in that case, C Twiddle, it'll be literally an unbranched cover. It'll just be the disjoint union of n copies of the complex plane. So in that case, so I told you that the GL1 Skein algebra, basically all that it keeps track of is the homology of the links. So in this case, homology, and so the GL1 Skein algebra of C Twiddle cross R is literally just Laurent polynomials in parameter Q. And then saying that this map FQ is a homomorphism is enough to tell you what it is. That fixes it, and it fixes it to be the Humphrey polynomial of the link evaluated at Q minus Q inverse. And so the Humphrey polynomial is a polynomial in Z and A, and so you have to specialize those values. Okay, so you recover just the Humphrey polynomial. That's not something new. But what's a little bit interesting about it is that the way that you get it, you get a new recipe for the Humphrey polynomial. So, or for the specialization of the Humphrey polynomial. So I want to show you that. Okay, so luckily my computer is working again, so I think I can show you this. Let's try it. So, oh, you have to make me host again. Sorry about that. Since I left and reconnected.
I'll help. Samuel, can you please do this?
Now I think I got it. Okay, good. So, okay, so now you see a picture of a link in R3. Do you see a picture?
Yes.
Okay, okay, good. So, okay, so this is a picture of the sort of the simplest example of this story. So I've got some unknot, you know, kind of polynomial unknot, which is the thing you see in blue. It's drawn in R3, and we're thinking of the case where, again, our base surface is just C, and we're just taking constant one forms giving the covering. So what those constant one forms produce for us concretely is some foliation of the plane. In this case, we just have two one forms. Their difference gives us a foliation of R3 by lines. And so these black lines are three leaves of that foliation. They're exactly the three leaves the only leaves which connect two distinct points of the link. And so if I apply literally our rules in this setting, what they say I have to do is I have to sum over all possible ways of lifting this link to the covering. Well, the covering just has two globally disconnected sheets. So that just means I'm labeling each strand of the link by either a 0 or a 1. So here's a picture of one such lift. Let's see, let me try to draw it so that it looks like the one I had before. Yeah, that's a projection like the one we had before. And so you see that most of the link in this picture is being lifted to sheet 1. That's what those little orange ones represent. And then there's a small part of it which is being lifted to sheet 0 up here. And then there's this movement where the 1 and 0 swap, they exchange with each other. That's what that's this like. So that's the position of one of these almost special Lagrangian strips that make the exchange. Okay, so in this particular case, we get, I think, 5 such lifts. Let's see. Yeah, it says there's a total of 5 ways of labeling the link with such a lift. You sum up all their contributions, and you get, no surprise, q plus 1 over q, which is the unnormalized Jones polynomial for the unknot, which is what you're supposed to get in this case. Now, this is not a surprise at all. In fact, you can see how you recover the usual, or one of the standard ways of computing the Jones polynomial, if I tilt this thing so that the exchanges are pointing kind of into the board. So since I've only one foliation here, I can just arrange it so that that foliation is pointing into the board. Now that's what I've done. I've kind of tilted it that way. And so now
Andy, sorry, I'm not understanding. Is the starting point of the construction a projection of the knot to a plane?
No, no, no. The starting point is not a projection of the knot to a plane. The starting point is the link in R3 together with the choice of this double covering of R3 lying inside the cotangent bundle of R3. Now, what's true is in the very special case of 2 sheets, if I want to give a covering like that with no branch points or anything, the data that I need, right? Those 2 sheets are just going to give me 2 points of the cotangent bundle, right? Which is, and if I want them to be constant, it's like 2 constant one forms. Now, of course, then the difference of those 2 one forms gives me a single one form. If I use the metric, I can turn that one form into a vector. So now I just have a vector. And using that vector, I can make a projection to R3. So that data determines a projection to R3. So in this case, we're going to recover something standard, exactly in this special case. Because the whole data is indeed, in this case, even though it's described differently, I guess it is more or less equivalent to just giving one projection. So that's what we're going to get here, right? So now I'm drawing it. I'm rotating this picture so that it's literally drawn relative to that projection. And then, of course, then what we get is something that's standard. Namely, we sum over all the labelings of the link with either a 1 or a 0, where the labeling is allowed to change only at the crossings. And at each crossing, there's some factor associated with how it changes. So that's called the Vertex model for computing the Jones polynomial. That's a standard thing. So in this case, we just recover the standard thing. So now, do the next one. Okay, so now I want to do the case with 3 sheets. And so this is the first case where we're going to get something new. So now I've drawn another picture of an unknot. And now, because we have this 3-sheeted covering, again, you could think of each sheet as giving you like a constant 1 form. And taking their differences, I get 3 constant 1 forms, or dually 3 vector fields. So now I have, so to speak, 3 projections. So you could say that the data is, you're given the link in R3 together with 3 projections. And now you're going to do a computation that uses all the projections. So now it can't be described just in terms of a single knot diagram. You have to use all 3 of them. But the rules are, again, that you have to sum up over all of these exchanges and higher webs that I described for you before. So here I've got, again, some unknot, some particular unknot, and for this particular one, with the particular foliations that we chose, there are a bunch of these kind of exchanges, and then there is a few of these kind of higher webs appearing. And so in this case, you have to sum up over all their contributions, and again, you get, okay, no big surprise, you get the Homfley polynomial for the unknot, this particular specialization. And then, just so that you don't think that it's only about the unknot, I'll show you one more. Here's an example of a trefoil with some huge pile of these webs, which you carefully sum up over, and you get the, as you must, you get the link polynomial for the trefoil. Okay, so what happened here? Okay, now, unless there are more questions about this picture, now I'll go back to the.
How do you count the Lagrangian disk? You actually have to solve the equation for a special Lagrangian strip?
Yeah, you actually have to solve the equation. But in this case, as it turns out, I didn't, for a long time, we didn't realize that it was going to be possible to actually do this, but you can actually do it.
That's because the geometry is so simple?
It's not really because, okay, it's definitely easier because we're doing it just in R3. I mean, literally,
Yeah,
I mean,
usually
I can phrase
finding
the
a
question.
special Lagrangian is not a trivial thing.
No, that's right. So here, so here it's very helpful that we're doing this. First of all, that we're doing this kind of degenerate limit where the special Lagrangians project to just these networks. And second of all, we're doing the case where everything's just in R3, there are branch points to worry about. Now, I mean, we've also done examples with branch points, of course, but then, as you say, it's much more elaborate. There's many more things that you have to deal with. Here in R3, it's still not a trivial problem, right? I mean, what we're doing here is we have to find all of the kind of webs that you can draw, where each leg of the web is pointing in some fixed standard direction, and all the endpoints of the web are on your given. It's not so easy to find all those, but it turns out that can be done by a computer.
Is it manifest that you get? Go ahead.
No, you go ahead, Mina.
Okay. Is it manifest that you get an invariant of knots in 3-dimensional space?
Is it manifest?
Yeah.
It's, I mean, it would be manifest from the theorem I told you, because, the Skein module by definition is like all these lengths up to isotopy and modulo these kind of moves. So the question is, how do we prove that theorem, right? And so to do that, no, it's not manifest. You have to check a bunch of kind of Reidemeister kind of moves. Absolutely. Good. Other questions? Okay. I mean, from the physical setup, it's somehow manifest. But to actually mechanically check it, right, to make it into a theorem, you have to check all the Reidemeister moves. Okay, so go on. I have to stop that. Okay. Okay, so that's the first sort of that's the first little application of this thing, is that it gives you even in the very baby case of unramified covers, it gives you of course the old link invariants, but it gives them to you in a new way. So then you can say, what about more general surfaces and links inside of C cross R? So then this FQ of L is, well, it's a new kind of link invariant. It is invariant for links not in R3, but in the surface cross R. I have to put invariant in quotes because it's actually not an invariant. So it depends on the covering C twiddle. So in this baby case of R3, it didn't depend on C twiddle, but in general, it really depends on C twiddle. Now it depends on it in a kind of controlled way. So there's a wall crossing formula that tells you, C twiddle. In other words, as you move around in the Coulomb branch of your n equals 2 theory, how this invariant changes. So in physics, we would call this invariant protected spin character. And now exactly what I call it now actually depends a little bit on whether my link can be drawn flat surface, or whether when I project it to C it has crossings. So if it has no crossings, then it's just a bunch of it's just a simple closed curve on the surface, and then it's a half BPS line defect. So from this point of view, what we're computing is the BPS states, including their spins, for these half BPS line defects. But more generally, if it has crossings, it's a slightly more exotic object. It's a quarter BPS object of line defect. So these are objects which, from the point of view of the n equals 2 theory, from the class S theory, you don't usually consider them because they break the rotation invariance a little bit. So if you picture this, a line defect, usually think of as like a particle in a four-dimensional theory. You think of a line defect as like a particle that's sitting at a point of space, a point of R3. And we usually consider line defects when we talk about, particularly when we talk about half BPS line defect, we're always talking about ones which preserve the whole group of rotations. In principle, there's no reason why a line defect has to preserve all the rotations. These fat line defects are ones which don't preserve all the rotations. They only preserve a U1. So again, if I take a link, which is a special link, which just comes from a simple closed curve on the surface, then it's an ordinary half BPS line defect. If I take a more general thing in this R, which is allowed to have some crossings, then it's not a half BPS line defect, but it is this quarter BPS fat line defect. So one physical interpretation of this invariant is that it's computing the protected spin character of these kinds of defects. Another thing we can say about this is, so another use map is that we can use it to construct representations of the Skein algebra. So the Skein algebra, the GLN Skein algebra of a surface is, as far as I understand, a relatively complicated object. It's hard to understand it. One of the first ways you want to understand some algebra is to construct representations of it. Here, once you have a map from the algebra out to something simpler, you can construct representations of it just by composing with representations of that simpler thing. So this is a way of kind of getting a handle on the representation theory of the Skein algebra. Okay, and then maybe just the last thing I'll say is that, well, since our construction is complete only for n equals, make this statement only for n equals 2, but it's surely supposed to be true in general. The construction that we do, even when we do it on a surface cross R, it's actually kind of three-dimensionally covariant. It's formulated in a way that doesn't really use the projection, the fact that it's C cross R. And so you're extending it to more general three manifolds, to understand the Skein modules of three manifolds. Okay. Yeah. I think maybe that's enough. So, so I think I'll leave it there. Thank you.
Okay, thank you, Andy. Are there any questions?
Yeah, I have a small question. I'm just, so in this last uses of FQ, I'm trying to understand the second point better, and in terms of class S theory. So, I have this link in C cross R. I choose a point in the Coulomb branch, some generic point. Then computing this new link invariant at that point is essentially as difficult as computing a BPS mass of some BPS state, or?
No. I mean, the BPS masses here are just the periods of the
exactly of well, H1 of your C tilde.
Yeah, I mean, maybe I should write kind of what the shape of the thing would be in that case, right? So, so the kind of expression you would get would be, let me write a sort of random example. So suppose that suppose we're in some example where the spectral cover has genus 1. Then the GL1 Skein algebra of C Twiddle is, generated by two variables, say x and y, with xy is q squared yx. This corresponds to two generators of homology. And so in this case, this link invariant, FQ of L, what it's going to be is it's going to be some Laurent polynomial so in R3, right, the usual link invariants are just Laurent polynomials in a variable q. Now here, we're going to get a polynomial in q, but also including these non-commuting x and y variables. So, it might be something like q plus q inverse, q times x plus, well, let's make it, suppose I make it one of these half BPS ones, then it always has the symmetry between q and q inverse. In fact, they're characters of SU2. So q squared plus 1 plus q to the minus 2 times x plus maybe, I don't know, q plus q inverse times y. It could be something like that. So the usual link invariants, right, are just polynomials in q. Here you get a polynomial in q, including these quantum torus variables that have to do with homology of this covering.
Of the of the infrared curve. I mean, this is the pure SU2 Seiberg-Witten picture, basically.
I mean, it could be the pure SU2. So the pure SU2, indeed, then the thing would have genus 1. Then C Twiddle would have genus 1.
Yeah. Wait, so but how does this depend on? So the way FQL is written, it only depends on the GL1 Skein algebra of C tilde.
Well, it lives in the GL1 Skein algebra of C Twiddle. So it's a map. Let me go back to what this FQ is. So FQ is a map which lands in the GL1 Skein algebra of C Twiddle. So the nature of the answer will be some element in there. It'll be some element in there. And so a typical element in there is something like what I wrote down here. It's some polynomial, the right polynomial in the variable q, and also the non-commuting variables x and y.
But then, okay, so can one see the effect of C tilde being in a particular chamber in the wall and chamber structure on the Coulomb?
Well, so as you change C Twiddle, as you change C twiddle, the answer will change. So maybe this is in one chamber. So maybe the answer is like this in one chamber.
Okay. I mean, the answer is locally constant. That's the.
It's locally constant, absolutely. So as you move around, so as you change C twiddle, the answer is kind of locally constant as a function of C twiddle.
Mm-hmm. You don't need to jump at the walls. That's the standard picture, but that means somehow this GL1 Skein algebra is jumping along the walls. I mean,
no, not the algebra. No, just the elements. You're just taking some particular element of that algebra, and that element jumps. But the algebra itself does not jump.
I see. That's a topological thing. That's fixed, but the elements in there. Okay, good. Thank you.
Well, wait a moment. If the BPS degeneracies jump and you make a cluster transformation on X and Y, it's invariant. So
that's right. That's right. When you make the quantum cluster transformation, yeah.
Yes, a quantum cluster transformation.
Cool. Thanks. I mean, it's obviously much more complicated when it's when C tilde has genus bigger than 1, simply because the BPS spectrum is a lot more complicated. I mean, in this case, it's just co-prime homology cycles.
Sure. These are the BPS spectrum here is the so-called framed BPS spectrum.
I see. Okay.
Even get very complicated, even for
genus 1 case.
Even for pure SU2 it's based on the link L.
I see. Okay.
Depending on what line defect you're looking at, even for pure SU2, the framed BPS spectrum can get rather complicated.
I see. And in particular, it depends on the link that was missing in the unframed picture.
Yeah, well, Andy wrote alpha of L.
By the way, I have to say, I never understood what that was. I wanted to ask that. That was in your initial conjecture. When you wrote the formula for, I think, FQ was sum over L tilde, alpha L tilde.
There should be, sorry.
Yeah, or here.
Sorry, you're absolutely right. This also depends on L.
I see.
Yeah, also up here.
Also upstairs, the theorem.
Right, of course, the L appears on the left side, has to also appear on the right side.
But how is the Z defined in the theorem above? The alpha L, essentially.
How was what defined? Oh, those integers?
Yeah.
In this case, those integers are, I mean, they're basically plus and minus 1. There's some tricky sign that you have to keep track of, but there's nothing very interesting in those integers in that case.
Okay. Okay. Well, that's okay. In particular, they're just plus minus 1.
There are some.
Well, okay.
There are some physicists.
Each L twiddle
physicists in the audience. It might help to say that L tilde is the infrared charge, that L is the UV line defect, and that alpha of L tilde L is the protected spin character for that charge.
Absolutely.
Mm.
Well, be careful. It's the sum up that alpha over all of the guys with the same homology class, and then it becomes the protected spin character.
Oh, okay. Yes. Yeah.
Is this some okay?
If we go back to the torus example that you did
this one at the bottom.
Yeah.
This thing.
Yeah. So suppose you construct a link that's contractible.
Yes.
In other words, it doesn't really see the torus at all. Would you still have dependence on X and Y?
No. Then you just get, if it sits inside of a little ball, then you just get the usual homily for that. It doesn't know about the rest of the surface. Although even that comes out in a quite complicated way, right? When you do it in examples, because there may be a lot of contributions from branch points which all cancel each other. But you're right. At the end of the day, if you can put your link inside of some ball in C cross R, then the answer that you get is just exactly the same as R. Okay,
so maybe here you want to say that even if we were to go back to Chern-Simons theory and what it means in Chern-Simons theory, that if you were to ask an analogous question in Chern-Simons theory, then the link invariant is not a number, it's more naturally an operator, and that's what you're writing. Is that what we're trying to say? We could have asked the same question, right, from perspective of Chern-Simons. In fact, there's a beautiful paper by Greg and I think Elitzer and Seiberg from very old days, where they construct canonical quantization of Chern-Simons theory, in particular on T2 times R. So you could actually, do the calculation there.
Yeah, but so what question exactly you want to ask?
We want to compute. We want to we want to check your answer from Chern-Simons theory. It's known, of course.
Well, I don't think so.
Well, the question can be posed, and it must be answerable as well, right?
Well, I'm actually not so sure how to state this, like this answer here, this FQ of L.
I think that's what it must be. Suppose you take Chern-Simons theory on T2 times R, and you add say just an unknown that wraps one cycle, and ask, so what's that? I think you would say that it's an operator. That's an operator like X, or an operator like Y, that correspond to holonomies of the Chern-Simons gauge field around the A cycle or the B cycle. And if you have a general link, you'll get you'll get something like that. So one should be able to compare this, which is nice.
I mean, what this is a kind of, okay, maybe I'll just say the same thing you said, but let me say the way I understand it. What this has to do with is a kind of comparison between two different Chern-Simons theories. So one of them is the Chern-Simons theory with gauge group GLN on some 3 manifold. Another one is the Chern-Simons theory with gauge group GL1 on this covering space. So.
But I thought we were trying to answer the GLN question using the GL1 theory. Right?
Well, okay, so. Of course, it's true that this Skein algebra is, of course, the algebra of operators in the Chern-Simons theory. Or it's the algebra of operators in the Chern-Simons theory at kind of generic Q. So if you like, we could say that we're trying to describe in a more efficient way the algebra of operators by relating it to the algebra of operators in GL1. Oh yeah, maybe that's what you were saying. Yeah, I agree. I mean, this is kind of like, the Skein algebra just is like the universal relations that the operators in Chern-Simons obey. I guess, yeah. Sorry, I guess that's what you said. Sorry, I agree with you. You're trying to describe it, but the question is kind of a funny question, right? It's not a partition function or something. It's a question of the relations among operators in the Chern-Simons theory.
Yeah, right. It sounds like that's what it is.
But yeah, so I agree.
Do you expect to be able to construct any representation of the GLN Skein algebra through the representation of GL1 Skein algebra on the cover?
Do you expect to get every representation that way?
Yeah.
Unfortunately, no. So the story is that, okay, so this is the question about which representations can you hope to get? So there's one very interesting representation of the Skein algebra. If you take Q to be a root of unity, there's a finite dimensional representation, which is the Hilbert space of the compact group Chern-Simons theory on your surface C.
Right.
Now, and so one thing you might like is to gain some understanding of that representation through this construction. Now, well, do you get that or don't you? So the good news is, okay, when Q is a root of unity, the Skein algebra has a very large center. There's a lot of elements in there that commute with everything, and so you can study the representation theory kind of sheafified over the center, meaning fix how the center acts. And the center is actually again a kind of classical Skein algebra. It looks a little weird at first, but you can explain this. So the representations of this Skein algebra kind of sheafify over the character variety, meaning for every point of the character variety, you can ask for the representations where the center X in a way dictated by that point. And then you can study essentially, you can use the Q to construct all the representations at kind of generic points of the character variety through this Abelianization. But the representation that you would be most interested in from the point of view of Chern-Simons, at least naively, is the one sitting over the identity. So the Chern-Simon, the one that Witten studied, is sitting over the identity, the most singular point of the character variety. And so you can't directly access it by this Abelianization. Still, there seems to be an interesting story where the representations that you can study form a kind of brain over the moduli of, they form a brain over the character variety, which is a BBB brain, one of these hyperholomorphic brains. So this is the subject of some project that we're trying to do with Faye and Greg Moore. So I think what we can certainly do is construct all the representations, with some work. What we'll be able to do is to construct all the representations away from the identity. Then you would like to somehow degenerate them into the representation at the identity. That part is not quite as clear.
And you're saying that it's the representation at the identity that's the representation of the Chern-Simons theory?
That's the one which actually comes from compact group Chern-Simons theory. So, yeah. So all this stuff, generic values of generic character for the center is somehow about the complex group Chern-Simons. What you'd like maybe is to learn something about the compact group Chern-Simons, and that seems.
You can recover everything about a compact. For not invariants of compact Chern-Simons theory come from quantum groups, and quantum groups make perfect sense at arbitrary Q. So you will never, in particular, right? As long as the questions are about not in link invariants, what a Q is cannot possibly matter. I mean, unless you want to start truncating representations and so forth, but it won't enter in any interesting way.
I mean, the kind of question that you might like to answer, which I don't think the answer is known, is whether the Hitchin connection on the bundle of Chern-Simons Hilbert spaces for compact group, whether that connection is unitary or not. It's not exactly a question about non-invariance, but it's the kind of thing that you would have a chance of understanding if you have some construction which naturally endows that space with a metric. Now, realizing it coming as one of the fibers of some BBB brain over the moduli of over the character variety is equipping all of the other fibers with a distinguished metric. So one might dream that in this way you're also going to fiber over the identity with a metric. If that works, then that metric, I would bet, is going to be the one that makes the thing unitary. That's the kind of question that I'm interested in answering. I don't know, I'm not saying I have all the answers.
And you expect it, I mean, then you expect the identity, sorry, the trivial representation and the corresponding unitary structure that you get on let me just call them conformal blocks, that they would be invariant under the mapping class group action as well. So you define this bundle of conformal blocks on the Teichmuller space, and the bundle turns out to be equivariant with respect to the mapping class group. So it descends to MG and gives the vector bundle. So you want, I mean, you want the Hermitian metric to be invariant under the mapping class group action as well. But if you can even just write down the unitary or Hermitian metric first, that would be quite something. Even if it is not a
right. I mean, the construction I'm suggesting wouldn't be on Teichmuller space. It would be directly on moduli space. So the question of whether it's mapping class group invariant somehow wouldn't arise. But I think I may be getting too far out over my skis. I just want to say what kind of thing representations I want to access.
No. Even on the moduli space, the question would become that the monodromy of the connection has a unitary representation, or it lies in the unitary group.
Oh, that's right. That's the question I want to ask. Is the connection unitary or not?
Right. Okay. Sorry. Yeah.
I had a question about, so you formulated this, so you started with a map between the character varieties, and then you quantized it by, but you gave it as a map between algebras. So geometrically, like, what are those spaces? Like, is they're moduli of something as well?
Yeah, algebra. Well, it's a non-commutative algebra, right? So it's not literally it's not a space in the conventional sense somehow.
Like, can I think, I mean, I started with moduli of connections. Can I think I'm studying moduli of something?
No, particularly it's not the same as studying, I mean, there's another deformation of this that you might have thought is the right one that has to do with, instead of studying flat connections, with studying difference equations.
Right, because you started off mentioning q-Wkv, which sounds like it should be about something like that, right?
Well, okay. You know, this story admits a lot of different deformations.
Right, of course.
The one that how can I say? I think the one that I'm most interested in at the moment is one where you have both h bar and q together. There are other things that one could do.
I guess my question is, like, so this story is this story supposed to be related to q-Wkv, or is that a separate kind of?
It's supposed to be related, but I mean, in this talk, I told you various things, right? I told you about exact Wkv. I told you about this Abelianization and its q deformation. I didn't tell you how to take that q deformation back to the exact Wkv story. I think it's a interesting question to which I personally don't know the answer. I can say some things about it, but
yeah, okay, thanks.
Right. Can you please tell us a little bit more about this 1/4 BPS line defect that you mentioned briefly?
Oh yeah. Yeah. So I mean, the picture is. Let me say it in kind of the class S language. I have to say it in class S language. So, you know, the usual kind of class S picture is that you take the 2, 0 theory and you formulate it on C cross R3, 1, right? And the conventional way of producing supersymmetric line defects in that theory is to take the surface defect of the 2, 0 theory and put it on, say, L cross, let's just say x1 equals x2 equals x3 equals 0. So in other words, this is a line inside of R3, 1, just like sitting at the origin of space. And then here you just take a simple closed curve. So that's the usual classification of line defects in say let's say just for the simplest case of A1. Then this is literally the classification of all the line defects by Drucker, Morrison, and Okuda, is that they correspond to simple closed curves on C. All the half BPS line defects, and the sort of 2, 0 origin of that is to take the surface defect on L, the simple closed curve, cross a line in space. So that's the usual half BPS situation. But there's another thing you could do, which is, let me divide this thing up a little differently into C cross R comma. And now I'll just take some link. Sorry. Again, I'll take the surface defect on some L here cross, again, a line now inside of R2 comma 1. So we've taken one of the dimensions that we usually think of as a dimension of space, and we're including it in the internal part. But what we should know about this L is that it only moves a tiny bit in that extra R, and only when necessary to avoid a crossing. So, you know, think of having a diagram of this link projected to C. It almost lies flat on C, but every time it has a crossing, it moves just a tiny bit in this X3 direction. So we could say this is the kind of X3 direction. And here is X1, X2, and X0. It moves just a tiny bit in the X3 direction to avoid the. Now, so that object doesn't look exactly like it's localized on a line in 4 dimensions, right? Because it moves a tiny bit in the X3 direction. But in the infrared limit, you know, so imagine you do that construction in the UV, and now you look at very long distances. The fact that it has some slight finite extent in the X3 direction will get compressed down to 0. And so the support of the object in 4 dimensions still looks like a point. On the other hand, it absolutely broke the rotation invariance. The fact that it was in X3 direction and not in the other 3 directions. The fact that it was extended a little bit in the X3 direction broke the rotation invariance, and the rotation invariance doesn't have to be restored in the limit, in the infrared limit. So what you get is a line defect which lives at a point, but which maybe breaks rotation invariance. And when you compute its BPS states, you see that in general, it does break the rotation invariance. The manifestation of that is that the symmetry between Q and Q inverse is broken. So for actual line defects, for the half BPS line defects, you always have that symmetry between Q and Q inverse in the spin character. In fact, it comes from a representation of the whole SO3. But here, in this slightly more general situation, the line defect breaks rotation invariance, and so it doesn't have this symmetry between Q and Q inverse anymore.
Does this also come in families labeled by some parameter? Does this type of line defect?
Oh, I forget about this. Yeah, you're asking if it has the same like zeta that you have for the. I forget how. God, I'm sorry. I forget how the subalgebra is. I forget what choices you have to make to get the subalgebra that it presents.
That's good. Thanks.
Yeah, sorry about that.
All right, any more questions?
So, I mean, only if you have a very quick answer because everybody's tired and so am I. But there was this very curious assumption that you made in the beginning that that your C needs to have a CP1 structure.
Why was it there?
Yeah, I mean, obviously you did everything else for CP1, or at least in my mind it was for CP1, but it's a kind of a curious thing that where would you use that?
Oh, you need that in order to even formulate the equation. So if you want to define like carefully what you mean by a meromorphic Schrodinger equation, you can write an equation which is locally given by the formula that I wrote, del squared plus you know, p equals 0. But now you want to make that global on the Riemann surface. That equation is not covariant on a general Riemann surface. Even if you make p a quadratic differential and psi a section of k to the minus a half, then you can make it almost covariant. But strictly speaking, it's only covariant under Mobius transformations, not arbitrary changes of coordinate. And so for that reason, in order to make sense of that equation, you have to first choose a chart of coordinate systems that differ only by Mobius transformations. And that's a CP1 structure.
Right. But I mean, okay.
Really
So
small technical.
So I remember, I mean, my CP1 structures is from the Thurston world where he said that the set of CP1 structures is equivalent to the Teichmuller space cross-measured eliminations. But there's also a characterization of CP1 structures in terms of affine SL2C connections. So I don't think it's true, but is the connection that you're building out here, the Nabla H flat SL2C connection, That depends on the projected.
Yeah, I mean, these are complex predictive structures. So if I took p equals 0, I'm getting the complex predictive structure that you're thinking of.
Yeah.
And then if I take p to be not 0, then I'm just shifting it
by this.
But that's right. It's the same story.
Cool. And this is really the last one and only if you have a very quick answer. Can you go up, please?
Oh, up here?
Yeah, here, right there. So I'm only asking this because I've seen this in a lot of talks and I've never seen an explicit expression for these functions Sn. So for example, if you, you start off on CP1, but your PZ has 4 zeros. So the covering is an elliptic curve punctured because your PZ needs to have poles as well. Then these Sn functions should be some classical elliptic functions written on your elliptic curve. And if yes, are they known? I mean, at least in some case, they should be known.
No, they're given by completely universal formulas just in terms of this p, whatever it is. So like for example, S1 is p prime divided by 4p, and S2 is some complicated thing, and it's like p double prime plus 5p prime squared or something like that.
So it's always the rational function in derivatives and powers of p.
Yeah.
I see. So
that's part of the power of the method somehow, is that they're given by this totally universal algebraic thing, which doesn't involve doing any integrals. The idea is to get rid of all the integration except for the simple abelian integral over your surface.
Mm-hmm. So initially when you started talking, I wanted to construct examples in my mind, and I wanted to, but I think this will not work, and this happened later. If you take PZ, so for example, you want to consider the situation where you have a hypergeometric equation on CP1. So your PZ should have 3 zeros.
Yeah.
But I think, so my question this is my ignorance, would the pole order 2 condition be satisfied in the hypergeometric case?
I think so, yeah. The hypergeometric occasion is one of the very few cases where the functions actually do have names.
These Sn functions have names?
No, not those. Just the solution. The solution has a name.
Well, that would be the hypergeometric
right.
But somehow with h bar in it, that's the.
No, I think in that case, the role of h bar is relatively mild. It just rescales the parameter. You know, in the hypergeometric equation, you have all these parameters, right? And I think h bar just enters in rescaling those parameters.
I see. Is the hypergeometric part written up somewhere?
Someone must have. Yeah. You're asking what happens if you literally apply exactly this method, the CP1 with 3 punctures.
Yeah. Basically, you take PZ polynomial to be the hypergeometric equation.
Right. Now, I don't know where someone has written out exactly that example in this language. It would be a good exercise to do it, I think.
Okay. So I have a meeting with some landlord. Thank you very much. It was great, and thank you organizers as well. Now, see you later. Thank you so much.
Thanks.
All right. Thanks, Andy.
Bye-bye.
Thanks for doing this. It was great having you.
Thanks.
Thank you.
All right. Thanks, everyone.